My name's Ross Grassie. I'm the Technical Program Manager for the Quantum Software Lab based at the University of Edinburgh. And today I'm going to talk about our work into quantum generative modeling and its applications. I'm going to start with just a bit of motivation of why we might take a quantum approach to generative modeling before going through some of the technical background of our core solution. I will then show how this solution is being applied both to financial use cases and in the field of genomics. But first, I want to start by asking some basic questions. What, why, when, who, and how? So what do we mean by generative modeling? Well, we can think of having our input as some samples from an unknown probability distribution. We want to take this, put it into our machine, and then that will output some algorithm that is able to produce new samples from this unknown probability distribution. Classically, we can do this using a tensor network. However, when we're taking a quantum approach, we'll put a parameterized quantum circuit in its place. And why might we want to do this? Well, there's the usual range of reasons that we may take a quantum approach. We might see some energy efficiency. Maybe it might be more accurate or speed. But today I want to talk predominantly about the expressivity. Can our quantum model give us probability distributions that we cannot reach classically? As a very rough timeline of when people started thinking about quantum generative modeling, I've listed some of the companies and universities that are doing this type of research. This is not exhaustive. I know that there are other people in the field. These are just the ones that we're mainly drawing from. Starting back in 2017, there was work on quantum circuit-borne machines, which I will mainly concentrate on today, but there's also been papers more recently by Quantinuum and QCware looking at quantum transformers as well. Now, how do these quantum circuit-borne machines work? We're going to set up some parameterized quantum circuit, and when we measure at the end, we'll get some binary string, and our probability of producing a particular binary string is going to be given by the Born rule, hence Born machine. Now the objective is that we want to make this probability distribution match that unknown probability distribution from our target data. Now we can do this comparison with a number of different divergences. We will mainly focus on using the maximum mean discrepancy. Now that we've covered a bit of motivation, I want to go through some of the technical background, in particular looking at the different parameterized quantum circuits that we're using, how we are training these parameters, and how we're thinking about the expressivity of these models. In our first use case, we use a hardware efficient ansatz, where we see we've got one layer of single qubit gates followed by 2 qubit gates, which are chosen to match the hardware architecture that we're going to be running this circuit on. So for instance, this 2 qubit gate here between qubit 20 and 21 is precisely because we have an edge between these 2 qubits in our topology. In the second use case that we'll see, we replaced the hardware efficient ansatz with a data re-uploading model, which is slightly different, where in each layer, we first set out our parameterized gates, and then we load some data using an encoding circuit. And the way that we train the parameters is we start off with some initial guess. This might be a random choice. This might be motivated if we have some domain knowledge about the problem that we're looking at. We're then going to put this into our parameterized quantum circuit that we've chosen. and we're going to run that n times to collect this data x. We've also got our target data set as well. We kind of get that for free because that's what we're trying to model. But then for each parameter that we have in our circuit, we're going to also have to run it another 2n times because we're going to use the parameter shift rule when we're calculating our gradients. So we take all of this data that we have here, put it together, and we're going to use that to calculate the gradients of our cost function. In the case where we're looking at the maximum mean discrepancy, this is some function where it's acting on a kernel which is taking various combinations of these vectors up here. In our case, we're just using a Gaussian kernel because these can be computed classically so that this computation is all done on a classical computer, saving us on quantum resource. So we calculate these gradients, take the initial parameters, put it into an optimizer, and that will suggest new parameters, and we keep doing this cycle until our cost function converges. In terms of expressivity, in the hardware efficient ansatz, there's not much that we can do other than just add more layers of the standard setup. However, when we're using the data re-uploading model, we can be a bit more nuanced in how we're thinking about expressivity. So we can think of this data re-uploading model working as having some Gaussian noise, which will be the data that we're inputting. We will then put this through our circuit, and that is going to generate a new distribution which has been modified from the initial one. We then compare this generated distribution against our target, and then we update the parameters for the next round as we saw on the slide before. So we can decide what kind of distributions we're going to allow by looking at our encoding circuit, and in particular in these Hamiltonians at the top here. Now, we can see this if we think of a Fourier decomposition of our parametrized quantum circuit. And we can see that the range of functions that we're able to capture is really kind of encoded in this big omega here. If this is large, then we're going to be able to be very expressive with our function. If there's only two terms in here, then there's a very limited number of functions that we'll be able to express. And this quantity is just given by the difference of these large lambdas here, which themselves are just a linear combination of the eigenvalues from these encoding Hamiltonians. So in this way, there's a direct relationship between how we choose these encoding Hamiltonians and how we can modify our distribution. And we want to play with these encoding Hamiltonians in such a way that we're not too expressive, so we run into barren plateau problems, but we're also expressive enough that we're able to capture the unknown target distribution. So now that I've gone through some of the technical aspects of our solution, we can have a look at our first use case, which is trying to learn correlations between different currency pairs. So the aim in this project is to generate high quality market data in foreign exchange markets. And if we can produce high quality market data to train our price prediction models, then in theory our price predictions will be better and we'll be able to make more money. So that's the motivation. So the data that we have here is 4 real value currency pairs that will all be highly correlated. And the real value is converted into a binary variable with up to 16 bits worth of precision. And we can make this problem more or less difficult by adding in more currency pairs or by making our approximation of the price more precise. So the setup in this case is that we have some probability distribution, which is given by some open source market data. We will then train our quantum circuit born machine, where we're using the hardware efficient ansatz in this case, and instead of the maximum mean discrepancy, we're using the sinkhorn divergence. The two are very closely equivalent. And then this is going to give us a new probability distribution. We then ask a random forest to try and tell the difference between samples from our new distribution and from the original distribution. If the discriminator error is large, then it means that our quantum circuit Born machine is producing new data points that look like the original market data. So we have higher quality market data. We're also going to train a classical equivalent, which is a restricted Boltzmann machine, so that we have a quantum classical comparison. Now, in these results, we show the discriminator error plotted against the number of epochs that we used when training this circuit. So the higher the discriminator error, the better the model is performing. And these pairs here just mean that we are looking at two currency pairs on this side here. And this is telling us the number of bits of precision that we're using when we're approximating the price. So 2, 3, 4, and 6 bits of precision, respectively. We can see that when we're not being too precise, we only have 2 or 3 bits, both models perform equivalently. But then when we start to get to 4 bits of precision and 6 bits, this purple line, which is the quantum solution, notably starts to perform better than the classical equivalent. Similarly, on the right-hand side here, we look at 3 currency pairs and 4 currency pairs with 2 bits of precision here and 4 for this top graph and 3 for the bottom one. Again, we can see that it doesn't matter too much how many currency pairs we're looking at. However, when we're looking at 4 bits of precision, the quantum yellow solution, again, notably performs better. So in these instances here, we begin to see that our quantum model is actually producing higher quality market data than the classical equivalent. So we have some evidence that a quantum approach is sensible here. So that was about a year ago. We have now picked up this kind of core toolkit, and we're now applying it to a genomics use case, where we're switching out the ansatz from this hardware efficient one to the data re-uploading model. And here we're trying to capture high order dependencies in gene expression. So talking to researchers in classical bioinformatics at the University of Edinburgh, they have a very nice model where what they do is they take in genomic data, they find genomic markers, and then these markers are able to determine different cell types and cell states. Now, this is very important when you're looking at finding cancer cells, or if you're thinking about personalized medicine and people's individual susceptibility to different diseases. So biological data is very hard to come by. You need to go into the lab. It takes a very long time to get all of this data. But we really want to find lots of these genomic markers to find different cell types and their cell states. So what we can think of doing is using a generative model to create synthetic gene data, which will be able to find markers when we come along new biological data. So that's what we're wanting to do here. However, biological data is very difficult to work with. So we're going to start off by using a toy example for the biological data, which is this 1D transverse Ising model. And we're doing this to ensure that we're confident that our quantum circuit Born machine is working before we then put it onto the unknown case in the biological data. And we can see from these results it is working quite nicely. So in particular, because the Ising model has an analytic form for its probability distribution, we can consider these blue lines here as a ground truth, and then the Born machine is how we are performing against the probability distribution. We can then take this probability distribution and calculate the 1, 2, and 3-point interactions within the chain, which is going to tell us how well it's actually capturing all of these different interactions, and we can see it performs relatively well. We also ran this on IBM's quantum computer, and when we run on QPU with circuit optimizations and quantum error mitigation, we see some nice agreement with an exact solver as well. So now that we've got to this stage, we can think of moving on to actual biological data with our model. Unfortunately, we got those results right after the slides were due in, so you can find those online. However, we are in the middle of training on real genomic data. The difficulty when we're using real data is that it's a very small sample size and it's very unstructured data. We find that when you're looking at the transverse Ising model, the data is very structured. That's much easier to train on. When you look at real biological data, that becomes much more difficult. But this work is now complete. We also want to be using that toolkit of looking at the different encoding Hamiltonians to make sure that we're only capturing the probability distributions that are required for us to get the biological data. And once we've done this, we want to revisit our financial use case, because we had our basic model, we've developed it by going over to genomics. Now we want to go back and see how it's performing on the financial data set. I think this is a really nice example of how, by working on core quantum algorithms and then thinking of applying them in different sectors, we can help each of those sectors kind of grow together so that both the finance and genomic practitioners can both reach practical quantum advantage together. So, thank you.
Thank you for your great presentation, Ross. それでは会場の皆様よりご質問一つもしございましたら。
We would like to accept one question from the floor. Any takers? No questions? Okay. Oh, yes. We have a question from the audience.
More about how to avoid the Baron-Plateau problem on the optimization of your quantum circuit.
Yes, it's very difficult. So actually, there's a very nice paper out from the group quite recently where it's using this toolkit of looking at the Fourier coefficients, and they're able to theoretically diagnose when you'll get barren plateaus and when you won't find barren plateaus. So that was another motivation for using this toolkit, because we have the theory which says, okay, if you try and make it so expressive by, I can't remember the exact results off the top of my head, but yeah, and we have that toolkit, and that's what we're using to try and avoid these barren plateaus. I can link you the paper.